Welcome to lesson number 8 in our series on the link layer as part of our course Networks and Distributed Systems, based on the textbook by Jim Couros and Keith Ross, Computer Networking, a Top-Down Approach. Having covered broadcast networks and multiple access protocols in the previous section, now we'll discuss switched local networks. Figure 5.15 shows a switched local network connecting 3 departments, 2 servers, and a router with 4 switches. Because these switches operate at the link layer, they switch link layer frames rather than network layer datagrams. They don't recognize network layer addresses, and they don't use routing algorithms like RIP or OSPF to determine paths through the network layer 2 switches. Instead of using IP addresses, they use link layer addresses to forward link layer frames through the network of switches. Remember, these switches do not communicate over the internet. These will all be found in autonomous systems. Hosts and routers have link layer addresses. Hosts and routers have network layer addresses as well. So why in the world do we need to have addresses at both the network and the link layers? In truth, it is not the hosts and routers that have link layer addresses, but rather it's their adapters or network interfaces that have those addresses. These days, a network interface is built into the system board of your computer, but some of us old-timers remember having to buy a special card called a network interface card for our computers. Most hosts have a single network adapter built into the system board. So, if you want multiple network interfaces for your own computer, you would normally have to buy one of these network interface cards. It's important to note that link layer switches do not have link layer addresses associated with their interfaces. This is because the job of the link layer switch is to carry datagrams between the host and routers. And the switch does this job transparently. That is, it does it without the host or router having to explicitly address the frame to the intervening switch. This is illustrated in Figure 5.16. A link layer address is called a LAN address or a physical address or a MAC address. Because the MAC address seems to be the most popular term, we'll refer to the link layer addresses as MAC addresses. For most LANs, including Ethernet and 802.11 wireless LANs, the MAC address is 6 bytes long, giving 248 possible MAC addresses. As shown in Figure 5.16, these 6-byte addresses are typically expressed in hexadecimal notation, with each byte of the address expressed as a pair of hexadecimal numbers. No 2 adapters have the same MAC address. Now, how is that possible? The answer is that IEEE manages the MAC address space. A company will purchase a chunk of address space consisting of 224 addresses for a price. IEEE allocates the chunk of 224 addresses by fixing the first 24 bits of a MAC address, or the first 3 pair of hexadecimal numbers, and letting the company create unique combinations of the last 24 bits or the last 3 pair of hexadecimal numbers for each adapter. This means that each adapter has a unique address. That is, the first 3 pair of hexadecimal numbers identify the manufacturer, and the last 3 numbers are unique to that manufacturer, making the whole MAC address unique. An adapter's MAC address has a flat structure as opposed to a hierarchical structure and doesn't change. A laptop with an Ethernet interface always has the same MAC address no matter where it goes. A smartphone with an 802.11 interface always has the same MAC address no matter where the smartphone goes. Remember that in contrast, IP addresses have a hierarchical structure. That is, they have a network part and a host part. And a host's IP address needs to be changed when the host moves. In other words, when it changes the network to which it's attached, the IP address changes. An adapter's MAC address is analogous to a person's social security number, which also has a flat addressing structure and which doesn't change no matter where that person goes. An IP address is analogous to a person's home street address or postal address, which is hierarchical and which must be changed whenever a person moves. Just as a person may find it useful to have both a postal address and a social security number, it is useful for a host and a router interface to have both network address and MAC address. That hierarchical structure of an IP address is what allows messages to navigate from host to destination regardless of where either happen to be. Just like the postal address allows a letter to reach you from anywhere in the world. When an adapter wants to send a frame to some destination adapter, the sending adapter inserts the destination adapter's MAC address into the frame and sends the frame into the local area network. A switch occasionally broadcasts an incoming frame to all of its interfaces. So an adapter may receive a frame that isn't addressed to it. When an adapter receives a frame, it will check to see whether the destination MAC address in the frame matches its own MAC address. If there's a match, the adapter extracts the enclosed datagram and passes the datagram up the protocol stack. If there isn't a match, the adapter discards the frame without passing the network layer datagram up. Therefore, the destination host will only be interrupted when the frame is received. Remember that it's the adapter doing all this work, and the host is unaware of all this taking place unless it gets that match of those MAC addresses. However, sometimes a sending adapter does not want all the adapters on the local area network to receive and process the frame that it is about to send. In this case, the sending adapter inserts a special MAC broadcast address into the destination address field of the frame. For LANs that use 6-byte addresses such as Ethernet and 802.11, the broadcast address is a string of 48 consecutive ones. That is FF, 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 FF. And in case you missed that, FS is a hexadecimal number, and there were 6 of them. Because there are both network layer addresses, IP addresses, and link layer addresses, MAC addresses, there is a need to translate between them. For the Internet, this is the job of the Address Resolution Protocol, ARP. To understand the need for a protocol such as ARP, consider the network diagram shown in this figure on your screen. In this simple example, each host and router has a single IP address and a single MAC address. As usual, IP addresses are shown in dotted decimal notation and MAC addresses are shown in hexadecimal notation. For the purposes of this discussion, we will assume that the switch broadcasts all frames. That is, whenever a switch receives a frame on one interface, it forwards the frame to all other interfaces. We'll soon find out why that's not true. Now suppose that the host with IP address 222.222.222.220 wants to send an IP datagram to host 222.222.222.222. In this example, both the source and destination are in the same subnet. To send a datagram, the source must give the adapter not only the IP datagram, but also the MAC address for the destination at IP address 222.222.222.222. The sending adapter will then construct a link layer frame containing the destination's MAC address and send the frame into the local area network. The important question in this section is, how does the sending host determine the MAC address to the destination host with the IP address 222.222.222.222? It uses ARP. An ARP module in the sending host takes an IP address on the same LAN as input and returns the corresponding MAC address. In this example, the sending host 222.222.222.220 provided its ARP module with the IP address 222.222.222.222, and the ARP module returned the corresponding MAC address 49 BD D2 C7 562A, 6 hexadecimal numbers. So we see that ARP resolves an IP address to a MAC address. In many ways, this is analogous to DNS, Domain Name System. You recall our discussion of that from a previous module. It resolves host names like Amazon.com to IP addresses, to whatever the Amazon's IP address is. However, one important difference between the two resolvers is that DNS resolves host name for host anywhere in the internet. ARP resolves IP addresses only for host and router interfaces on the same subnet. It does not go to the internet. If a node in California were to try to use ARP to resolve an IP address for a node in Mississippi, ARP would return an error message. Now that we have explained what ARP does, let's look at how it works. Each host and router has an ARP table in memory, which contains the mappings of IP addresses to MAC addresses. The ARP table also contains a time to live value, which indicates when each mapping will be deleted from the table. Note that a table does not necessarily contain an entry for every host and router on the subnet. Some may have never been entered into the table, and others may have expired. A typical expiration time for an entry is 20 minutes from when an entry is placed in the ARP table. Now suppose that host 222.222.222.220 wants to send a datagram that is IP addressed to another host or router on that subnet. The sending host needs to obtain the MAC address of the destination given the IP address. This task is easy if the sender's ARP table has an entry for the destination node. But what if it doesn't? Suppose that 222.222.222.220 wants to send a datagram to 222.222.222.222. The sender uses the ARP protocol to resolve the address. First, the sender constructs a special packet called an ARP packet, and an ARP packet has several fields, including sending and receiving IP and MAC addresses. Both ARP and query response packets have the same format. The purpose of the ARP query packet is to query all other hosts and routers on the subnet to determine the MAC address corresponding to the IP address that is being resolved. Returning to our example, 222.222.222.220 passes an ARP query packet to the adapter along with an indication that the adapter should send the packet to the MAC broadcast address, namely all those FFs in hexadecimal are all ones. The adapter encapsulates the ARP packet in a link layer frame, uses the broadcast address for the frame's destination address, and transmits the frame into the subnet. The frame containing the ARP query is received by all the other adapters on the subnet, and each adapter passes that ARP packet within the frame up to its ARP module. Each of those ARP modules checks to see if its IP address matches the destination IP address of the ARP packet. The one with a match sends back to the querying host a response ARP packet with the desired mapping. The querying host 222.222.222.220 can then update its ARP table and send its datagram encapsulated in a link layer frame whose destination MAC is that of the host or router responding to that earlier ARP query. There's a couple of interesting things to note about the ARP protocol. First, the query ARP message is sent within a broadcast frame, whereas the response ARP message is sent within a standard frame. Second, ARP is plug and play. That is, an ARP table gets built automatically. It doesn't have to be configured by a system administrator. And if a host becomes disconnected from the subnet, its entry is eventually deleted from other ARP tables in the subnet. The ARP packet is encapsulated within a link layer frame and therefore lies architecturally above the link layer. However, the ARP packet has fields containing link layer addresses and therefore is arguably a link layer protocol. But it also contains network layer address and therefore it could be argued that it's a network layer protocol. In the end, ARP is probably best considered to be a protocol that more or less straddles the boundary between the link and network layers, not really fitting into a simple layered protocol stack. Before we start talking about how a host on one subnet sends a frame to a host on a different subnet, let's take a break. Review your notes, update your study guide, and come on back and we will continue on.